We are in Chapter 4, Exponential and Logarithmic Functions. Section 4.1 is Exponential Functions and Continuous Compoundings. So this should be a review section for us. If you struggle with anything or if you don't remember certain things and you need some additional help, definitely reach out either to myself or to the MARC Center or ASAC, and they'll also be able to help kind of refresh this idea for you and make sure that you're good. So we need these concepts in order to do the calculus stuff, but this is an algebra section. So first thing that we have is exponential functions, which is f of x equals a to the x, where a is greater than 0 and not equal to 1. And so you can see we have two different graphs that are given here. The first graph here would be an exponential growth model, and the other one would be an exponential decay model. But you'll notice that for both of these, the domain is going to be all real numbers. So the domain for both of these functions, depending on what model you have, if it's growing or if it's decaying, is going to be from negative infinity to positive infinity. And then our range, if you notice for both of these, is nothing negatives, and 0 is actually a horizontal asymptote. So this is going to go from 0 to infinity. And then we have a y-intercept for both of these also. And that y-intercept is going to be that point, if you see it on both these graphs, at 0, 1. And so again, this is for both of these graphs, not just for one of them. Right below this, it says the rules for exponential numbers are summarized below. And we did see these earlier in the semester, so they are rewritten here for us. Exponent rule, so if a and b are positive numbers and x and y are any real numbers, then b to the x plus y is the same thing as b to the x times b to the y. B to the x minus y is the same thing as b to the x over b to the y. B to the x to the y is the same as b to the x times y. AB to the x is the same as a to the x, b to the x. And a divided by b raised to the x power is the same as a to the x over b to the x. And then the last one down here states that for b not equal to 1, b to the x equals b to the y if and only if x is equal to y. So the next thing that we have is an example that says evaluate the given expressions. Answers should not contain any negative or rational exponents. So again, rational just means fractions. Part A says 3 to the second raised to the 5 over 2 power. And looking at our properties up above, you'll see that you multiply your exponents. And so those would reduce, and we would end up with 3 to the 5th power, which you can input in on your calculator, and this is going to be 243. Part B says 3 to the 1.2 times 3 to the 2.7 divided by 3 to the 4.1. First thing to note is that all the bases are 3's, which means that we're able to use those exponent rules to combine them. So looking at the numerator, I would add those exponents together and we get 3 to the 3.9 power divided by 3 to the 4.1. From here we would subtract these, again using our properties listed up above. Subtracting these, we have 3 to the 3.9 minus 4.1, which is going to be 3 to the negative 0.2, which is going to equal to 3 to the negative 1/5. If we write that as a fraction exponent or as a rational exponent, since it's negative, this would move to the denominator. And that 1/5 is the same thing as a 5th root. So this would be the same as 1 over the 5th root of 3. And that would be our final answer. Part C says negative 2x to the negative third times 3x to the 2/3 is going to be, in that negative 2 times 3, we just multiply like negative numbers, so that would be negative 6. Since the bases are x, we have a negative third and a positive 2/3, and so I need to combine those. I'm going to do my work over here on the side. You can definitely use your calculator, but negative 3 plus 2 over 3, getting a common denominator, I need to multiply the first fraction by 3 over 3. And so we end up with negative 9/3 plus 2/3, which is going to work out to be negative 7/3. And so this is going to be negative 7/3 And again, since it's negative, it would move to the denominator. The 6 is negative, but the exponent on the 6 is technically a 1, so that does stay in the numerator. So we have negative 6 over positive x to the 7/3. And then rewriting this with a root, remember the top number stays with that value, so it's going to be x to the 7th. And the denominator on that exponent will become our root, so the 3rd root. And that would be our final answer. Part D says x to the 3rd, y to the negative 2nd, over z to the 4th, all raised to the 1/6 power. So that 1/6 has to go to every single variable that we have, and we have to multiply those exponents. So we're going to have x to the 3rd times 1/6, y to the negative 2 times 1/6, over z to the 4th times 1/6. Just writing this out a little bit more so we can see the work. From here, we have x to the 1/2, y to the negative 1/3, and all over z to the 4/6, which reduces to 2/3. So from here, I notice that my y can move to the denominator. And so we have x to the 1/2 all over y to the 1/3, z to the 2/3. The exponent on both y and z have the same denominator. And so I'm going to go ahead and combine those together and say x to the 1/2 all over y to the 1st, z to the 2nd, all raised to the 1/3. And then rewriting this without those rational exponents or those fractions, we have the square root of x over the cube root of, and it's y z to the 2nd. So that would be our final answer with no rational or negative exponents. So the next thing that we have is an application of this. This is called the future value of an investment. Compound interest. If P dollars are invested at a yearly interest rate R, compounded in times per year for T years, the compounded amount in the account after T years is A equals P times 1 plus R over N raised to the NT power. A equals PE to the RT power. And so let's talk about what this means here. So if you have money and you're going to invest it at a bank, you get what's called interest. And so that interest is going to be a little bit of money that the bank gives you for letting them borrow your money. And they put it into your account. And normally for banks, it's done quarterly, so it's done 4 times a year. However, there are banks that might do things a little different. They might do it annually, semi-annually, things like that. And also a little bit different for investments. The other one that we have is continuous compoundings, which means that continuously all throughout, so right now, they're putting that money into your account. So your account grows even though you're not putting any additional money in. And so for us, the number of compoundings per year is going to be stated in the problem. And so first thing to note is that T is equal in years. And so sometimes they'll say it's half a year or 6 months, and so T would be 0.5 or 1/2. And R is going to be your interest rate, but you need to make sure you state this as a decimal. The other thing to note in these formulas, especially for this first one that we have, is N. And N is the number of compoundings per year. And so we'll talk about some of the more widely used wording that we might see in problems. But if you see something different, definitely add it to this list. So we might see the word annually. And for annually, that would be just 1 compounding per year. So that means N would be equal to 1. Another widely used one is going to be semi-annually. And this would be N is equal to 2. A big one that we do see, like we stated earlier, is going to be quarterly. And N is equal to 4. There's 4 quarters in a year. Another big one that we see is monthly. And that would be N is equal to 12. And continuing my list over on the right side, I'm going to also put down daily as a big one that we see. And daily is equal to 365. So it's how many times that occurs in 1 year. So monthly there's 12, quarterly there's 4, semi-annually would be 2, daily 365, and again annually it would be just 1. So carefully reading those problems, looking for those words, and then remembering what that means, which is the number of compoundings per year, and thinking about what N would be. So the example right below says, suppose $5,000 is invested at an annual interest rate of 10%. Compute the future value of the investment after 8 years if the interest is compounded, and it does say round to the nearest cent since we are dealing with money. Again, we're investing this for 8 years. We have $5,000 and its interest rate is 10%. So the first thing that we have, part A says annually, and so I'm going to go ahead and write down my formula, which is up above, since we are compounding this. I'm going to use that first equation that we have. And so P is principal, that's what you're starting with. That's the P dollars that are invested as stated up above. And so for us, our P here is going to be 5,000. Our interest rate R is going to be 10%, but written as a decimal be 0.10. And then T is 8. And so substituting these all in, we have 5,000 times 1 plus R, which is 0.10 over N. And for this problem, since we are dealing with annually, N is going to be equal to 1. And then raised to the N, which is 1, times T, which again is 8. And then from here you can substitute this all in on your calculator. Again, we're rounding to the nearest cent, so 2 decimal places. And this works out to being $10,717.94. So 10% interest rate is very far from what we have right now. But with this, we have $5,000 we're investing. 8 years later, we come back to the bank, and we now have $10,717.94. So big increase here. So semi-annually, now they're going to take that interest, and rather than giving it to you all at the end of the year, they're going to give you some of it in the middle of the year and then some at the end of the year, so twice. So you should have more money in your account because it's being compounded more often. And so from here, since semi-annually, this means N is equal to 2. I'm going to go ahead and substitute all these values into my formula. So we still have $5,000. We have 10% interest, or 0.10. This time it's divided by 2. Raised to the N, which is 2, and T, which is 8. Substituting this into our calculator and working this out, rounding 2 decimal places, we get $10,914.37. So yes, it is a little bit more. I would take the extra almost $200 easily. That's a lot. So you can see that as you increase your compoundings, you do increase the amount of money that you would have in your account. Part C says daily, and it says not a leap year. So every now and then you'll see something that says leap year, and that would be where N would be 366 with that extra day. But for us, it's going to be 365, which is typically what we would have. So A is going to be equal to 5,000. 1 plus R, which is 0.10, divided by N, which is 365, raised to the 365 times 8. And so again, this time daily, so every day they put a little bit of money into your account, so it's growing. And so we would again have more money than what we would have had in part A and even in part B. And so working this out on our calculator and substituting this all in, we get $11,126.49. So again, this is an increase from what we had for part A and also for part B. Part D says continuous, and this time we have to use our continuous compoundings formula. And writing that down from up above, it's A equals PE to the RT power. A lot of students remember this as just saying PERT. And so P again is going to be our $5,000. E, R is equal to our rate, which is 0.10, and time here is 8. You'll notice that no, we do not have any compoundings because this is done continuously, and that's what that E in here is representing. You should have that E button, that exponential, on your calculator, so look for that. And substituting this all in, since we are continuously compounding, this should be the optimal return, meaning that this should be the most amount of money that we could receive. So working this out, we get $11,127.70. So not too much more than daily, but definitely a little bit more, and I would again take that money also. So right below this we have what's called present value of an investment. And so for present value of an investment, the present value P of T of an investment A accumulated the annual interest rate R compounded n times per year over a time of T years is given by, and we have P of T. They also sometimes will write this as PV, meaning present value at time T, is equal to A times 1 plus R over N to the negative NT. And this also says if the interest is compounded continuously at the same annual rate R over the term of T years, the present value, if it's compounded continuously, is going to be P of T or PV of T for that present value, A e to the negative RT. And so A is equal to how much you will need after time T. So right below this we have another example. The next example says, Faye is about to enter college. When she graduates 4 years from now, she wants to take a trip to Europe that she estimates will cost $5,000. How much should she invest at 7% to have enough for the trip if interest is compounded? And part A says quarterly and B says continuously. And so for this, you'll notice that the wording now is that she wants to save up to have this money. So she needs to know how much to invest now in order to have that $5,000 in the future. So for this, the present value of T, or P of T, is going to be equal to, and the value that we have here for our formula is going to be A, which is how much you will need after time T, and she needs $5,000. So this is going to be our A. We also know that she wants to be able to go on this trip in 4 years, so that is going to be our T. And R is equal to 7% or 0.07. This also does say quarterly, so we know that N is equal to 4. So substituting everything into our formula, which is listed up above, we have A, which is 5,000, times 1 plus R, and R is 0.07, all over N, which is 4, raised to the, and it's a negative exponent, N is 4, and T, our time here, is 4 years, so 4. So from here we need to substitute this all in on our calculator. And when we do, we'll find out how much money she needs to put in the bank right now so that she has enough money in the future, that $5,000 in 4 years to take that trip to Europe. And so working this out, we get $3,788.08. So she needs to invest that right now in order to have enough money, which she needs is $5,000 in 4 years to take that trip. Part B is the same problem, but this time it's compounded quarterly. So if you notice, we'll be using a different formula. And so our PV of T, or P of T, for continuously is just A e to negative RT. So again, A is the amount that we would like to have, which is that $5,000. E to the negative R, which is 0.07, and then T again is 4 years. And so working this out on your calculator, and again rounding 2 decimal places since we are dealing with money, is going to be $3,778.92.